After a lot of research, I found the cleanest, most accurate EQ possible with any processor that's currently available. And honestly, I'm incredibly excited about this. So let's jump into how EQs are secretly changing dynamics, adding distortion and other unwanted artifacts, and then detail how to equalize with substantially fewer unwanted changes to the process signal. Now let's talk about the commonly known way that EQ alters dynamics. We don't think of EQ as altering the dynamic range, but it does it in a few ways. The first way is easiest to understand with an example. So say I'm EQing the kick, its overall dynamic range is -72 to -8 dB, with the fundamental causing this peak. Now if I amplify the fundamental with a bell by 3 dB, the peak should now be around -5 dB. The noise floor of the affected region will also be amplified by about 3 dB, with variation in how much is amplified due to the Q value, bell shape, etc. Now the noise floor of other areas, or most of the kick, won't be altered. So before, our range was -72 dB to -8 dB, or 64 dB in total. Our range now is -71 dB to -5 dB, which is 66 dB in total, since not all of the noise floor was amplified. Now this is all interesting and it's good to know, but admittedly, there is a much more hidden, rarely discussed way that EQs are messing with dynamics and not equalizing the way we think they do. So let's look behind the scenes of EQ. Right now we're looking at a sine wave with variable amplitudes. First it's quiet, then loud, then it's quiet again. When introducing a processor, we could observe any alterations to these levels. Let's introduce a high-pass filter at 40 Hz with a slope of 24 dB per octave. Note that the sine wave used by Plugin Doctor currently has a frequency of 2 kHz. So this filter should not impact the sine wave, but look at what happens. It's subtle, but the filter's introduction causes a modulating spike when the sine wave's amplitude is increased. It causes the same modulation in an equal and opposite manner when the signal's amplitude decreases. If we increase the filter's slope, the alteration becomes more aggressive. As I increase the cutoff frequency, closer and closer to the frequency of the sine wave, or 2 kHz, the distortion and subsequent alteration to the dynamics becomes more significant, with the most significant change occurring around 1.8 kHz. Additionally, notice that it takes roughly 20 milliseconds before the amplitude adjusts back to the intended value, definitely long enough to be noticeable. But as I've come to expect, this issue is even more prevalent in low frequencies. If I alter the sine wave to 88 Hz, then with the cutoff set around 60 Hz, we'll observe alterations to the amplitude just like before. However, instead of taking 20 milliseconds to return to the accurate amplitude, it takes close to half a second. And watch what happens as the cutoff approaches the sine wave's frequency. Again, with the cutoff at 80 Hz, we'd expect to see no alteration to the dynamics of a higher frequency. But the changes are significant and they only get weirder. With the cutoff at 90 Hz, notice this gradual amplification from the quiet section of the sine wave to the loud. Additionally, notice this massive amplitude change when transitioning from the loud section to the quiet. Now what do you think will happen if I move the high-pass filter way past the sine wave's frequency? If you think that it shouldn't have a signal, or you shouldn't be able to see one, I thought the same exact thing, because that makes sense. But when the cutoff is at 1 kHz, 88 Hz is still present and it's modulating whenever the signal's amplitude would have transitioned from quiet to loud. It is not until the cutoff approaches 23 kHz that we finally fully attenuated the signal. Now, if I had asked you, hey, how do I get rid of a signal around 90 Hz? I can't imagine that your answer, or anybody's answer, would have been to set a high-pass filter around 23 kHz. Now, is this issue fixed using linear phase filters? Well, no, not really, both regarding amplitude changes when the cutoff is set before the frequency and after. In fact, now in addition to post-ringing, we have pre-ringing distortion. Well, I've been using really high slopes for a while. What if I switch to a 6 dB per octave? Now it's better, but we still have weird modulation to the signal's amplitude occurring during any transition of the original sine wave's amplitude. And to cover all the bases, this happens with bell filters, notch filters, obviously low-pass filters, and more. Now maybe this all seems purely technical, but this issue has massive implications for how something sounds. To test it, I took a track and attempted to attenuate about 70 Hz and below with a high-pass filter. Using a null test between the original and the process signal, I should be able to hear the difference between the two. If the filter we're using is incredibly accurate and the processing doesn't make any other unintended alterations to the signal, then I should only hear 70 Hz and below. So let's listen to the differences between the original signal and the processed one when I use a minimum phase high-pass filter, then a linear phase high-pass filter, and lastly, the cleanest method that I've found, which I'm going to show you how to do in just a moment. If you want to get your mixes to sound like professional songs, we have a mixing membership called the Sage Audio Membership, where you get access to Sage Audio University for in-depth mixing and mastering courses, private one-on-one mentorship, unlimited personalized mixing feedback, and 50 free mastered songs per year. Go to sageaudio.com or use the link in the description. Now, you probably noticed the minimum phase filter wasn't accurate in the slightest. When we take a look at the waveforms, note that very little phase rotation is occurring at lower amplitudes, but once the amplitude increases, aggressive changes occur, just like what we observed with the sine wave. This continues throughout the song. The polarity is completely inverted in spots, the waveforms are shaped and seemingly have different amplitudes and behaviors. All in all, this simple filter completely alters the signal. Now imagine the implications of this when you're processing multiple instruments with various filters, different dynamics, etc. Meanwhile, the linear phase filter performed significantly better. The waveform doesn't give us any obvious indications of being altered in any way that we didn't intend. However, if you listened very carefully during the demo, you could hear quiet, high-frequency information, indicating that the filter is causing at least some unexpected changes to the signal. Now, the most accurate is this method, which is equalizing with isotope RX. So the RX platform isn't supposed to be an EQ. It's meant for surgical changes to audio, but its design offers a unique opportunity when you're mixing. With it, it's possible to highlight various aspects of the track over time and then affect them. I can't say this for certain, but my best guess is that when we process a track within this platform, we're not using certain filters, like with an EQ. We're altering information on a binary level. So, if I highlight and select all the information below 70 Hz and use the gain module to attenuate the highlighted region, the platform deletes the information associated with the frequency range. By deleting information instead of filtering, the process signal is not subjected to whatever unintended changes a filter might cause. So, say I want to amplify 3 kHz on the vocal by 2 dB. With the vocal file in RX, I'd use the frequency select tool to highlight the region. If I need to isolate a more specific range, I could zoom in using the vertical slider, scroll until I find the right range, highlight it, and then use the gain module to affect the region. I'll show you how to do this quickly in just a moment, but let's take a listen to this method being used on a vocal to cut frequencies below 80 Hz, reduce a narrow band of nasally tones by 5 dB, boost the range around 3 kHz by 3 dB, and then add 3 dB of air above 11 kHz.
I'll never know what I've never known. Let it go, float on the ocean. I'll never know what I've never known. Let it go, float on the ocean.
Last up, let's talk about quickly equalizing with isotope RX. So first off, a huge thank you to our viewer David for letting me know about this setup that I'm about to show you. This has saved me a lot of time, so I genuinely appreciate it. In short, RX could be set as the default editor in your DAW. In Logic, I enabled the advanced plugins, went to Audio, then Audio Editor, and then I selected RX as the external editor. So now if I want to use it to process a clip, I select the clip, hit Shift-W, and RX pops up. After I make the changes I want, I can select File, then overwrite the original file, and close out of RX. Logic then replaces the original clip with the processed one. If I decide at some point I need to revert back to the original, I could open RX again with Shift-W, click the initial state, overwrite the file, and close out, so this process isn't destructive to your files in any way. Now keep in mind that the changes applied with this method will occur before any of the inserts that are used in your DAW. And for that reason, I think this method is best suited for aggressive filtering, such as notch filters, high-pass and low-pass filters. So I'm going to perform a simple mix using this method for any aggressive filters I would have normally used. We'll A/B the same mix, but done with filters, or EQs, and let me know if one sounds better to you. As I mentioned earlier, if you want to get your mixes to sound like professional songs, we have a mixing membership called the Sage Audio Membership, where you get access to Sage Audio University for in-depth mixing and mastering courses, private one-on-one mentorship, unlimited personalized mixing feedback, and 50 free mastered songs per year. Go to sageaudio.com or use the link in the description.